Everyone, this is Chakradhar Konda. This is my presentation on the subject course CS513 Topics of Operating Systems, and the project name is Log Structured Non-Volatile Main Memory. Coming to the introduction part. Uh, Today we will explore the emerging NVMM, which is non-volatile main memory technologies such as 3D X-Point, PCM, STT RAM, and ReRAM. These technologies promise to enhance application performance by storing persistent data directly in main memory. However, this shift necessitates a lightweight, persistent transactional memory system to manage data access. We'll discuss the limitations of existing PTM systems such as memory fragmentation and excessive write traffic, and introduce a new log structured NVMM system that significantly improves transaction throughput and power write efficiency. Coming to the next slide, subject study objectives. Our study aimed to address several PTM issues. We designed a novel persistent memory-based PTM system called NVMM to overcome challenges like fragmentation, write loads, and persistent barriers. We sought to integrate the NVMM home space with the log area, reducing write traffic and eliminating persistent barriers and fragmentation. Additionally, we employed a tree-based address translation method to enhance memory operations and provide flexibility in access granularities. The next slide, address mapping. Address mapping is a unique feature in our log structure NVMM implementation. Unlike previous systems, NVMM employs a flat address space where allocation granularity doesn't necessarily match access granularity. We reduced a tree-based address mapping strategy, enabling mapping per use time rather than per allocation time, allowing arbitrary access and improving data retrieval efficiency. Next is optimizing the address mapping. In this slide, we optimize the address mapping through several methods. Two-layer mapping divides the home space into fixed length partitions, reducing tree height and improving lookup efficiency. Group updates merge contiguous writes, updating the tree only once to minimize tree updates and improve performance. Skip list serves as the tree data structure, avoiding complex rebalancing operations and reducing log contention in multi-thread scenarios. Tree node cache stores recently accessed nodes, reducing the need for the full tree lookups and improving performance for frequently accessed memory areas. So these are the 4 optimizing methods for address mappings. And coming to the next slide, which is organization and log structure of NVMM. At the physical level, the NVMM region is divided into static chunks, which can be chained by pointers to form a list. This design allows threads to select, allocate, or deallocate NVMM space with minimal competition. The log structure includes a list of chunks, enabling 1 or more logs per thread, which improves parallelism and log cleaning efficiency. Coming to the next slide, log cleaning, optimizing for efficiency. One of the critical components in our log structured NVMM system is the log cleaning process, which ensures that we maintain high performance and minimize fragmentation. Log cleaning is the process of reclaiming space taken up by absolute or stale log entries, and it's essential for long-term efficiency of the system. To optimize log cleaning, we implemented several techniques. First one is fast cleaning. This technique focuses on quickly reclaiming chunks that mostly contain mostly stale log entries instead of copying valid data to new locations. We simply adjust list pointers to exclude the stale chunks, significantly speeding up the cleaning process. This reduces the overhead and allows for faster reuse of memory. Second technique is separate logs for different operations. We maintain distinct logs for different stores, allocations, and reallocations. By separating these operations, we exploit their inherent locality and reduce the mixing of different types of data. This separation minimizes the amount of data that needs to be moved during cleaning, thereby improving efficiency. Third technique, which is parallel cleaning. To further enhance log cleaning, we use multiple thread to perform log cleaning operations in parallel. Each thread can work on different chunks or logs, increasing throughput and reducing the overall time required for cleaning. This parallelism is crucially in multi-core systems, where leveraging all available processing power can lead to significant performance gains. By employing these techniques, we can ensure our log-structured NVMM remain efficient and responsive, even as the volume of the data grows. The next slide is implementation of log-structured NVMM. Now let's delve into the specifics of how we implemented the log-structured NVMM. Our primary goal was to address several pressing issues related to NVMM memory management, such as fragmentation, wear, and the overhead associated with ensuring data persistence. Here are the key aspects of our implementation. First thing is integration of data home and log structures. Unlike traditional systems where data home, space, and log areas are separate, our approach integrates these structures with integration reduces the write traffic and eliminates the need for persistence barriers, which are typically required to ensure data consistency. By unifying these areas, we streamline memory management and enhance performance. Second one is memory allocators. For managing the home space, we use well-known memory allocators such as WOD and DL-malloc. These allocators are designed to be efficient and reduce fragmentation, make them suitable for NVMM implementation. Third one is transactional memory support. We leverage tiny STM, a software transactional memory system to handle transactional operations. Tiny STM ensures that memory operations within transactions are atomic and consistent, which are critical for maintaining data integrity in a persistent memory environment. Fourth one is persistence memory mechanism. Ensuring data persistence is a core requirement for NVMM. When a transaction commits, we flush the allocated memory and any writes to log into NVMM. This flushing guarantees that all changes made by transactions are durable even in the event of power failure. Through these implementation details, our log-structured NVMM system achieves high performance, reducing fragmentation, and improved wear leveling, addressing the major challenges faced by traditional PTM systems. Coming to the next slide, log space management. Effective log space management is crucial for performance and reliability of a log-structured NVMM system. Here is how we manage our log space. The first one is log entry. Each log entry consists of a header and an actual log data. The header contains the home address of the data, a tombstone flag indicating if the entry is obsolete, and the size of the entry. This structured approach follows allows us to efficiently manage and identify log entries. Second one is transaction blocks. A set of log entries related to a particular transaction is grouped into transaction blocks. Each block includes metadata that helps in verifying the integrity of the transaction, ensuring that all operations within the transactions are either fully completed or fully rolled back in the case of failure. Third one is chunks. Log entries and transaction blocks are stored within chunks. A chunk is a fixed size segment of memory, and multiple chunks are linked together to form a list. This design allows for flexible and scalable log space management. When a log entry is too large to fit into a single chunk, it can split across multiple chunks linked by pointers. By organizing the log space into entries, blocks, and chunks, we ensure efficient use of memory, quick access to log data, and easy management of memory allocation and deallocation. Coming to the next slide, the address mapping. Address mapping is a pivotal component of our log-structured NVMM systems, ensuring that we can efficiently locate and manage data. Our approach to address mapping includes several innovative techniques. The first one is skip lists for address mapping. Skip lists are used to map home addresses to log addresses. Unlike traditional data structures like binary trees, skip lists offer a balance between simplicity and performance. They support lock-free reads, which enhances concurrency and reduces contention in multi-threaded environments. Skip lists also provide efficient insertions and deletions, making them well suited for dynamic address mapping. Second one is concurrent operations. In a multi-threaded systems, it's essential to support the concurrent operations without significant performance penalties. By using skip lists, we enable lock-free reads, allowing multi-threads to access the address mapping concurrently. For updates, we use locking mechanisms to ensure data integrity while minimizing the congestion. Third one is tree node caches. To further optimize address mapping, we implement caches for recently accessed tree nodes. These caches store frequently accessed nodes, reducing the need for the full tree lookups and improving access time. By keeping hot data in the cache, we enhance the overall performance of the system. There's also like fourth step, dynamic address translation. Our address mapping strategy supports dynamic translation, allowing for flexible access granularity. This means that the system can adapt to varying size of data access requests, improving efficiency and reducing the overhead associated with fixed allocation sizes. Overall, our address mapping techniques ensure that the log-structured NVMM system can quickly and efficiently translate addresses, support high level of concurrency, and adapt to a varying data access patterns. Log cleaning. Log cleaning involves identifying victim chunks with high level of stale data. Cleaner threads transfer live data from victim chunks to other chunks, updating global mapping with new log addresses. And once all transaction blocks are moved, the victim chunk is reclaimed, which is chunk reclamation process, and made available for future use. Recovery. There are two phases of recovery performed. So first one is recovery threads process log chunks concurrently, collecting valid logs by home address partition. And the second phase is like each recovery thread handles specific home partitions, replaying logs based on home address and version number to reconstruct the address mapping tree. Evaluation or the experiment setup phase. In this, we're going to discuss, we conducted experiment on an 8-core Intel Xeon CPU with V3 server with 64 GB of DRAM running a 64-bit Linux kernel. Since real NVMe products aren't available, we use simulation techniques to mimic the impact of slow NVMe writes. Our benchmark suite included 5 transactional benchmarks covering common data structures and a key value store application. The effects of optimization. There are 5 effects we have noticed. We evaluated the effects for our optimizations. First one is baseline using global skip line list. Second one is two-layer mapping with partition skip list. Third one is like a group update for sequential writes. And fourth one is 2LGUC, which is thread local caches. Fifth one is for LSNVMM, avoids locking for read-only operations. You can see it avoids read-only operations. Our enhancement improves GPU utilization by up to 268.6% with an average increase of 157 of 9% compared to the baseline. Two-layer mapping, group update, and thread local cache, providing sustainable speedups, and LSNVMM further boost scalability by eliminating locking overhead for read-only operations. Comparison to current systems with our system, LSNM-VMM outperforms existing systems like Neon Misoi and MNSYY undo, reducing the average transaction time by 37.3% and 66.1% respectively with one thread. Minimosoin integrates redo logging and TinySTM, while the MNM SYN undo replaces redo logs with undo logs. LSNMVMM's log structure approaches provide superior performance. The write traffic and wear of the NVMM. The write traffic. LSNMVMM significantly reduces NVMM write traffic and wear compared to the both above discussed systems, Meonosyne and MNM SYN undo. LSNVMM achieves an average reduction in write traffic by 82.8% and 82.0% respectively. It also reduces dirty bytes by 80.1% and 65.1% on average, enhancing overall system efficiency and longevity. Fragmentation of NVMM. The fragmentation is minimized in LSNVMM compared to the Horde and Gmalloc systems. LSNMVMM achieves significantly lower fragmentation rates, reducing them to as low as 0.6 in some scenarios. Log cleaning. There are 2 steps, separate logs and baseline. Log cleaning in LSNVMM is highly efficient, capable of cleaning over 200 MB of memory per million updates. The separate log design allows for faster removal of chunks compared to the baseline, ensuring optimal memory utilization and performance. And next slide is like log-induced cost. LSNMVMM minimizes log-induced cost. The recovery process is efficient, completing in 3 seconds with 8 threads for 128 byte value. And the DRAM footprint is around 16.9% of NVMM when the value size is 128 bytes, decreasing quickly as the value size increases, demonstrating LSNMVMM's scalability and efficiency. The related work of our project is as discussed in this slide. LSNMVMM builds and on PTM techniques but follows a log structured approach for memory management compared to memory allocators like Makalu and WALOC, which focus on garbage collection and where labeling. LSNMVMM reduces memory fragmentation. Similar to RAM cloud, LSNMVMM aims to reduce fragmentation through log structure design but supports general transaction rather than just key value data. Log structure systems like LFS, F2FS, and NOVA shares principles with LSNMVMM, but our system's unique challenge lies in tree-based address translation. And coming to the last slide, conclusion of our project. In conclusion, our system LSNMVMM addresses critical issues like NVMM fragmentation and RAID, providing significant performance improvements. Our key optimizations tackles the challenge of tree-based address mappings, as we discussed, enabling efficient NVMM operations. Through extensive experiments, LSNMVMM outperforms prior systems like Neomosine and MNM SYN undo in transaction throughput. Future research will focus on scalability, energy consumption, reliability, long-term durability, and broader applicability of LSM NVMM. Future research implications, which can be further persisted. Like first one is scalability and complexity. What is performed in LSN MVM with large data sets and computation that are more intensive. Uh, will this future research will explore LSN VMM performance with large data sets and intensive computations. We'll examine if effects on energy use, system availability, and reliability under different loads. So the third one is like long-term durability. Additionally, we'll study the long-term durability of the NVMM for demanding tasks and optimizing LSNVMM for various applications, incorporating it with evolving hardware platforms. Future work could optimize like various uses. Thank you for your attention. This concludes our presentation on log structure NVMM, which is non-volatile main memory. If you have any questions, feel free to ask. Thank you.